First of all, thank you very much for having me over here. I'm Kenichi Soga from UC Berkeley in California, and it's great to be here. I was here about 15 years ago, and then I see such a development after 15 years. So I would say every time I see everything, we say, wow, wow, wow. So congratulations on that. What I want to do today is first thank colleagues from Encardio, Rite, the chairman, Arush, and Rafi. And then actually one of the reasons I'm here is that Rite, who's going to talk later on, was a student at UC Berkeley. And then professors tend to dream about things, but then Rite started to make things real happen. So I'm so happy to be here, and I'll try to show my best. So the talk of today is really about management, monitoring to management. So if you look at our infrastructure, as I'm a civil engineer, geotechnical engineer by training, we tend to design for 100 years, as you see over here. And then if you see the second column, if you're working as an infrastructure, you want to prolong the life of infrastructure. Most of the projects I was involved when I was at Cambridge University was in London, where we have old infrastructure. Now I moved to San Francisco Bay Area. We also have a lot of infrastructure, and we're struggling with those. I'm sure Dubai is expanding right now, but maybe 50 years, 100 years, you may start to see those that we're working on. And we don't want you to see something that we're suffering. So what can we do better? And then we see a demand. Dubai, I came here 20 years ago, was totally different. And then I'm sure 20 years from now, it's going to be different. So the demand changes more rapidly than our design life, or actually the life of the infrastructure. So how can we make our infrastructure design not like a rigid, but more adaptive to change? So that allows us to think we gotta sense what we're doing, what the performance of our infrastructure. And that leads to excitement in terms of sensors and data analytics that we see. But we wanna make sure that these sensors, data analytics, will last for 20 years, 30 years, 50 years. What kind of technologies can we make sure that it's gonna last for many years? So the point is that our 100 years design life may not be compatible with the actual demand in the future. We can think about our infrastructure adaptive to change rather than rigid in terms of design and construction. So let's imagine a world where future generations like Ritvik and other colleagues do not have to worry about aging infrastructure. So that is the spirit that I want to give you today. So first, excitement. Excitement is about the technology, emerging technologies. That's what we see over here in Dubai as well. This particular graph I made about 3 years ago, and I'm sure it's changing now, but vertical axis, expectation, horizontal axis, a time, and they're always a hype that goes up to the peak, and you can see AI, machine learning, a little bit going down maybe, but then there's a peak, and it goes down to bring it to the market. You see LiDAR, wireless sensor networks, drones. I see some of the demos in the other room. You see this happening in real environment right now. You see technical digital twin coming in, and this is part of the theme I think we're going to have today, but also distributed fiber optic sensing, which I'm going to talk a little bit more as well. And satellite systems. Sorry, it doesn't work here. And then you have a machine learning. And then the other thing I want to talk a little bit is about technical digital twin, but we call it social technical digital twin. How we bring social science into digital twin. And this is something I'll show you later on. Distributed means a lot of things. Distributed in space, from satellites, drones to sensors, and we go across different things. What excitement. This is one of the technology 20 years ago, one of my PhD students spin out to create a wireless sensor company. And Amit said that he's using the sensors right now in Dubai, so I'm so happy to see that. What allows you to do is you can monitor things. These are the modes that can talk to each other and hop, hop, hop like what you do with your Wi-Fi at home mesh network, but in a really large scale. It allows you to move and distribute in time. You can measure in a different time intervals. For example, you can have a low data sampling rate, maybe 1 hour, every sample every hour. And then if you use these batteries, theoretically it can last for 20 to 25 years. So you just leave it and then you can monitor for 20 to 25 years. Because most of the cases, it's not the device. It's the person changing the battery is the most expensive part. At the same time, you may want to measure acceleration or some noise that has a high frequency. In that case, battery cannot do very well. So you can start to think a little bit cleverly in terms of triggering when necessary. And these are triggering devices that you see. And then you save energy. But the point is the past 20 years, we spent a lot of time to say, how can we make it low power so that it can last for a long time? So that's exciting. Distributed sensors, this is some of the work we do on tunneling machine. You see Dubai Metro tunneling machine. Actually, this machine has 6,000 data sets every 2 centimeter or 1 centimeter moves. You've got lots of data that you can see on the right figure over there. These are selection of sensor data, but we have 6,000 of them. And we can start using those to understand what's in front of you, like your sort of automated cars, which is trying to use LiDAR and visuals to find out where you want to go. But in tunneling, you cannot see in the front, but you can use the information to see what is the ground that it's excavating. So this is really every borehole you have a ground truth, and as you move, you start to see what's the ground in between the boreholes. And you can see the green, the blue is clay soil, the orange is sandy soils, and this is what the AI or data analytics will tell us by 6,000 data sets as you learn along here. The one over the top shows what the engineering geologist trying to interpolate between the boreholes. And what you see is such a nice correspondence. If you look at the details, for example, you can see some pockets of certain different soils you see in sort of a green or purple, and actually you can see that through the machine learning technique, through the 6,000 borehole, 6,000 data sets. So that's exciting as well. So at UC Berkeley, we have a Center for Smart Infrastructure. It's really about partnership with infrastructure owners, academia, industry, regulators, to sort of address the most pressing challenges like aging infrastructure, climate change, water supply, natural resources, emergency and community preparedness. Especially in the Bay Area, we have earthquakes and wildfires, which I'll show you more later on. But the vision is to provide innovative solutions to realize adaptive system with intelligence for life. So make sure that we monitor our infrastructure until it will be reused, for example. So we work together with many infrastructure owners because infrastructure owners, if they believe, because if they tend to have a very long-term view, and therefore, if we work together, it will make it happen. One thing also we want to do is look at how data is used to interpret your asset through the digital twin, and then really about value of infrastructure. And we have to appreciate, and this is where I work with many of the general manager infrastructure owners, what are they thinking about? What are their drivers for economics, resilience, sustainability, equity, for example? And there are a lot of uncertainties that you see, perhaps like reputation, policy, stakeholders' expectations. As an engineer like me, are really looking at asset level about safety and asset management, obviously about life expectancy, risk assessment, risk mitigation, and cost-based analysis. Our job is really to link this through monitoring. But the monitoring is not really just to see what's going right now. What we want to do is to predict what's going to happen in the future, which allows you to give a project sort of a service performance, which allows the infrastructure owners to cope with sudden things that you never think of, and they're ready to act. So in our UC Berkeley, we have a lot of people working on it. At the service performance level, we have Sim Center, which is a simulation center, which I'll show you a little bit more later on. And my colleagues over here on the top are social scientists. Whereas on the bottom is really our engineers really looking at asset and then really linked together through large-scale test beds, showcasing we can do it. And hopefully what we want to do is to have this circular economy. That infrastructure is built, you operate, hopefully prolong the extend the life. And that's what we want to do. We want to live longer. But then think about rebuild and how can we use this data to make this happen. So what I'm trying to do next is to give you some examples. So this is just a vision, and what I'm going to show you is some of the examples. Smart construction. I'm happy to see a lot of things happening as a geotechnical engineer. It's a dream to be here in Dubai. A lot of piling, foundation, and all these things. And one of the technology that we've been using for the past 20 years is what we call distributed fiber optic sensing. It's a fiber optics. Maybe some of you have heard of it. Fiber optics, mostly used for telecommunication, for fiber optics communication, but actually fiber optic can become a sensor. You shoot a light, and then every point, a small light comes back. And if you analyze that small light coming back at different location, I can get what is the temperature at that point? What is the strain at that point? What is the vibration happening at that time? At every point along the fiber for tens of kilometers. So think about using this as a sensor for monitoring infrastructure. And this is called distributed fiber optic sensing. So I'm going to give you one example as a geotechnical engineer which may relate to you if you're a geotechnical engineer. This is a project in London, in Canary Wharf. There are buildings, as you can see, it's one of financial districts in London, in Canary Wharf. There are not many high-rise buildings like what you have over here in Dubai, but there are a lot of issues on ground. So typically here, you have a London Underground tunnel, old infrastructure, with the new piling going nearby. So it's very important to understand what is the pile-soil interaction. And I see this is like a sort of a pile of about 80 meters or so, and I'm sure in here you have that kind of a shaft and piles, large diameter piles. So in this particular project, we have a reinforced cage where we attach the optical fiber during construction. There are two cables attached. One is strain cables, and other is a temperature cable. And we attach the cable at different location on the cage, so the cable goes in and out to the surface, goes to a different location, go to the pile, and come up at different location of the pile in terms of temperature and strain. And the cable are connected together, and once you have this interrogator, I can get the temperature and strain at the same time during the loading. So this is the sort of pile load test, you know, the bidirectional loading test, or we call it O-cells that we measure. We have an expert here. We have a sort of an O-cell that pushes the pile upwards but pushes downwards. It's a self-reacting device, which is so good because if you just apply a load from the top, you need to have a huge reaction, whereas this is self-reaction. But it allows us to understand what is the shaft friction, meaning that what is the friction between the pile and the soil, and then what is the end bearing of the pile. It is important to make sure that these are installed in a good way, but also don't disturb the construction process. So this one, I have a drum of cables that you can see the drum of the cables that goes in as the cage goes down. Our contractors just attach the cable, hook it up, and then as it goes down and when cages are spliced, you hook it up and hook it up. And at the end, you pull it a little bit, and then you do the tremi-concreting. One thing that we always worry about is in terms of how the concrete are flowing when you do the concreting. So sometimes if the concrete doesn't flow well in the ground, you may have some pockets of not concreting going through. So what we tend to do is what we call thermal integrity test. Because the cable can measure temperature, I can see how the temperature is changing during the curing of the pile. And this one shows there are 4 cables in the pile at 4 different locations, 90 degrees. And you can see that they're sort of curing in a different way. As you can see that the blue and green is in one side, and the red and yellow is in the other side, meaning that curing is happening not uniformly in that. Also what you see is, I'm going to do it again, is that you see also this sort of a randomness in the data, but also up and downs in the data. In a sense that every 3 meters or so, there's something going on in terms of temperature variation during the curing. But what we can use is that from this temperature, how the temperature heat is dissipating into the ground, and this is called thermal integrity testing, is based on that, I can try to get a shape of the pile. So by looking at the temperature change with time and doing some analysis, I can get a shape of the pile. And this is called thermal integrity test. So this is the shape of the pile of this particular case. And then what you can do is that you can start to go to a deeper one and just to see how the shape of the pile looks like, just from measuring the temperature change. And you can say, wow, it looks good, maybe thin over here, thick over here. It's not a big variation, but you can see how it's performing. Now when you apply your load, so now you look at the pile, now you apply a load. So you can apply a load. And now you're applying a load at the bottom. Your strain will be the largest at the bottom and then decreases as it goes top because you have a frictional happening between the soil and the pile. And then this particular gradient is related to shaft friction. And what you see over here is that as you increase the load, this triangular distribution becomes sort of a bigger and bigger. Triangle will become bigger, meaning that the gradient is higher, means that there's more friction. So when you look at this particular data, it looks like this, like a triangular distribution, but it goes up and down. Do you like this data? Oh, that's good, because many designers say, I want this, not that. But the point is that the data is not just one data over here and one over here. It's lots of data creating the shape. And there's a lot of analysis we can do, but the point is that it's about 3 meters interval. That is related to how you do the concrete. You push your concrete, you bring your tube up 3 meters, and then you push it again. There's an interesting cross-section process that you can do. But then with these data sets, you can do a finite element analysis to get how the shaft friction is developing as a load. And these are called TZ relationship that we use in design. So you can derive the TZ relationship based on that. So this is excitement, is that with fiber optics, you can measure what is the real performance as a part of the construction control. You can see the real loading of the performance, and also future proofing. Perhaps there will be a new construction nearby in the future. You have a fiber optics already in your pile. So just hook it up, and then you see actually how pile is performing. And once you know the real performance, maybe you can reuse the pile. And that's something that many people in geotechnical engineering have been thinking about. And as a developer, that will become a very important part of the asset. The foundation becomes an asset for future development. So just one of the examples as excitement. Smart operation. We have a lot of water main breaks in the Bay Area just because many of the earthquakes and then ground landslides, and when it breaks, it goes like this, and then, and then you have to have a construction worker fixing it. It would be nice to have a robot that can fix this. but not yet, so I'm waiting for that. Now, this is the 30 years worth of, this is the Bay Area on the East Bay, and my campus is right over here. And you can see a lot of breaks in terms of corrosion or ground movement related ones. And then these are the data for the 30 years of the main breaks. So it's everywhere. After 150 years, 100 years, we get these breaks. The point is that there's about 1,000 breaks every year, about 3 break every day, and our construction crew needs to go and fix those. This is the history, and you can see that the first pipe were built in 1880s, 150 years ago. They used cast iron. Around World War II, after World War II, they decided to use asbestos cement pipe. And then after that, people start using steel pipe. And corrosion becomes an issue sometimes. And then you have a non-metallic one. The point here is that even 100-year design life, we tend to make our decision changing the life, how we're going to use different materials. So that's a problem. We've been really focusing on cast iron, but then the issue becomes asbestos now. So we start to see some asbestos pipe, which is a very big issue because once you're exposed to the air, asbestos comes into the particulate and becomes a health issue. So we're thinking how we can rehabilitate these ones. But the point is that this particular infrastructure is 100 years design life. This particular company called East Bay Municipality District, we call it East Bay Mud, about 42,000 miles, 4,200 miles of pipelines. It goes from San Francisco to Chicago and come back. That's the number of pipes, length of the pipe they have. They replace every 25 miles per 40 kilometers per year. It will take, just thinking about the cycle, it's going to take 150 to 200 years. So it's beyond that 100 years design life. So we're not doing, how can we do better? Obviously, one of our issues we have is that here we have a Hayward fault, which is one of the largest fault in system in the Bay Area. And our campus is over here. And then here's one of the pipe that crosses that Hayward fault. So what we tend to do is that we tend to use INSAR. So we do INSAR, and my colleagues over in Encardio also do a lot of INSAR measurements. So these are the INSAR measurements of the active landslides. We can detect where the active things are moving. At the same time, we have these ancient landslide as well, which may move after a big earthquake. So we tend to look at these, and then what we do is that we look at each pipeline and then see what kind of strain. If you can need movements, I can back calculate what kind of strain these pipes will happen, both in axial and bending. This is the picture of the pipeline in our area. And if you come to our campus, this is our campus. Our campus is in the what we call pink zone. And actually, this is a hill. So this is a Berkeley hill. So from the bay, it goes to the hill and goes to the other side of a hill. And we have a water treatment plant on the other side of the hill, which elevation is 107 meters. Our campus is on 109 meters. So in order to have enough pressure, every day water goes through the tunnel and goes up to these 2 water reservoirs, tanks. That will give enough pressure, 150 meters, to provide a pressure to this pink zone. And unfortunately, our fault right goes across here. So if earthquake happens, we have a risk. So here we put fiber optics. So this is a new pipeline crossing the Hayward fault, and we attach the optical fiber, like what you see over here. Some are in the trench, some are in the pipeline. You directly attach to see how these pipes are behaving. And actually, this fault is creeping with time, so we can see how much strain is developing on these pipes. So this is the picture of the trenching, and then some support, and you can see a pipe. And then when you see the video, how they install it, you can see the trench, and then the pipeline, and you see 3 lines silver lines, these are the fiber optic lines attached to these pipes. And we epoxy glue it, so hopefully it will last for 100 years, but we don't know yet. But then the point here is that you put these fiber while during construction. At every point along the fiber, I can measure strain. So the point is that we can do some analysis, we can do sort of a monitoring. The point here is that we do a lot of these simulations, assuming some assumptions. But let's go to here. And you see a pipe, but then if you see next to it, there's an abandoned pipe. At Berkeley or in the Bay Area, we don't take out the pipe, we just leave the pipe. So the question is that, is this pipe going to affect when my new pipe is affected by the earthquakes or fault zone? So the point here is that once a pipeline is buried, we're not going to see it for the next 100 years. The picture you see, probably you're not going to see again. So why not embed intelligence during construction for future generations? So what we're doing is that we've been monitoring that particular optic for about a year or so, and you can start to see that there are more strain developing at the fault zone areas. You can see it. And it's very small. It's only 100 microstrain. If you understand strain, I can integrate the strain to get the displacement. So relative displacement from one to the other. And this is what is showing. In 1 year, it moved from one side to the other side about 4 millimeter. So 150 meters pipe, I can see the little bit of elongation of 4 millimeter using this technology. So it's very sensitive, and you can start to see, like measuring your heartbeat, seeing what's going on in this infrastructure. The point here is that earthquake is going to happen, and then we want to see, and we design the pipeline to withstand sort of 30 centimeters movement. We believe that pipe will be okay, but then after an earthquake, we see how much strain it affected after an earthquake, and that gives us what we call residual strain, so we can say, when shall we replace the pipe? So that is a very important assessment to do. We also do satellite, so these are satellite data and trying to compare with that satellite data with the strain data, and they match very nicely. So these are the exciting part of these technologies. You can embed the fiber in the road. So this is a smart road that we have, and you can have your dog running. This is a PhD student called Peter, had a dog, but he graduated 5 years ago, so we don't have a dog anymore. So we have a Spot. And I think you have your old robotic dog as well. So now we use robotic dog to showcase. But then you can see the movement of the dog from the fiber optics. It's so sensitive. This is really, really small movements. Then you can start attaching these fibers. Your fiber is already in the road, for example, for telecommunication. You can attach the fiber on the pipeline. And then what you can start to do is start listening, because the fiber becomes microphone as well. So this is just an experiment. We were having a fun experiment in the actual pipeline. We start to create a fictitious leak. And I think you're going to hear a sound. So no leak yet. And then we start to open up the tap to make it a little bit leak. And you can start to hear the sound. This is measured by fiber optics. Obviously, the big one, you know, it's a big one already. But the idea is, can we detect before this happens through listening? And we do this technique for listening, but then fiber optic can become your microphone now. You can have a fiber optic. You already have a fiber optics along your street. It's called dark fiber, but used for telecommunication. So you can borrow one of the row. And here's one of the work that we're doing from city of Richmond to Oakland through this particular road, which is about 25 kilometers. So from Richmond all the way to Oakland, 25 kilometers along that road, and this is with minute-by-minute movement of what's happening on that particular road. And you see the lines, and this line corresponds to car moving on that road. So you can see a car started from this location, it moved with time in this direction, the gradient is the speed of the car. You can see some stopped, so no movement, and then start again. So you can see the activities of the sort of a road, and we're working with Caltran, California Transportation System. Can we detect heavy truckloads, EV cars? Can we detect people moving, road safety, and can we detect leakage of the pipelines? In the California coast, we have our wind farm will going to be floating structures, and there are moor lines. Oh, so we do a lot of testing of these moor lines, tension and compression, but also moor lines become a microphone to hear our whale singing. Again, that's recorded by fiber optics. So exciting for these, and these are coming into infrastructure market more and more. Smart data. So in the past, engineering design is something about we sort of know what's happening of our performance of infrastructure with time from our experience. We say, okay, this is statistically, and we may show that, okay, limit of unacceptable, factor safety, probabilistic, based on assumed failure mechanisms. And then we say, okay, if some accident happens, we say, wow, that's something I didn't think about it. So you recalibrate your probability to give a different factor safety. You may be surprises. You may have another accident and say, okay, I have to think about different mechanism, and you update your design. And this is called approach 1, managing safety by snapshot, setting a safety margin. And actually this particular concept comes from psychology. Professor Holneger from Denmark is a psychologist. He's looking at how to treat hospitals, how to run hospitals. And hospitals just don't use factor safety. They monitor how the doctors are running, how the caretakers are working, to how the patients are working in real time, so that you can be more proactive. So the point is that infrastructure, we tend to be like this, but then in the past it was too expensive to monitor, but I think with this technology we can do it. So this is called approach 2, managing safety by everyday work, real-time monitoring. You monitor, you learn, anticipate, and respond. So this is what you can do. You can monitor. So if you monitor, you can provide the accident not to happen because you're more proactive. So if you know the actual performance, you can learn how to respond quickly if an event begins to unfold. You manage future unknown demand by reducing the uncertainties. Perhaps there's some weather change happening in the past 20 years or so, which was not considered during the design stage. And then you identify potential improvements in the design and construction process. You can learn something, like the one that I showed you, the pile geometry and how shaft is developing. You start to learn, and you can start do better job in your design because you know the actual performance. And it can lead to circular economy, really about reusing the piles or reusing the component of our infrastructure because you know actual performance of the infrastructure you're dealing with. Obviously, that's what data and AI and machine learning is, and you're going to see here a lot of things probably from Rite and the others about the value over there. But the point is that many of the AI just look at the average. But what we want to do is to really looking at the tail ends, because engineers, as engineers, we're trained to look at what if happens in this way, how do we respond? So that's where your learning, anticipating, respond will come as a value. So sound engineering judgment leading to right choice and decision through the monitoring is what we want to train our young engineers. AI is exciting. My generation, I remember Minority Report. Some of you remember Minority Report? The movie is still movie. It's about finding the crime before the crime happens. So Tom Cruise comes, and then somebody wanted to stab somebody, but then Tom Cruise and then catch him or catch the sort of person who's trying to stab, and before the crime happens. So we want to do that for infrastructure. We want to do the infrastructure just before it breaks. We don't want to replace it when it's very, very nice. So how can we predict about the lifeline of our infrastructure? Typically in our mind, we tend to look at sort of a linearly, what is the age of the pipe, what is the material pipe, and we put weights. Because it's easy to look, and this is how we understand, and many of us work on this. Great thing about AI and machine learning is what your mind works as an expert is think differently in many ways, going back and forth. And that is the sort of strength of the AI. It's an emergent technologies, but how do we interpret, because it may become a black box. So the point here is that you may heard about random forest, neural networks, support vector machine, and all these things like many AI machine people lurk, and then it may confuse you, and many of us are confused because they use one technology and say, I'm good at that. Many of the infrastructure owners are coming to us and say, I really want to know what are they talking about. So we're opening up the sort of machine learning tools to figure out how can you make it better. So this is where we want to make sure that we guide our AI and machine learning specialists. We really understand, because we're not interested in just the average problem, we're interested in the tail ends. So just looking at that pipeline I showed you from the East Bay Mud, I showed you 1,000 breaks every year. And then we have lots of data for 30 years. And then if you have a lot of these pipelines and say, okay, one side pipeline is in the landslide, a fault zone, and not in the fault zone. If I spread the two categories, I can clearly see that if it's on the fault zone, the probability of failure with time, 50 years, 100 years, 150 years, because we have a data up to 150 years, I can get a prediction of how they're going to break. And then if it's not on the fault zone, it's less likely to break. If you're on the landslide, also I can see the difference. If the materials, I can see the difference. But the point is that I can separate you two, and you have certain categories, but every individual of you are different. So they're all combined together, and then I want you to be your pipeline and want to make sure how long you're going to last. That's something we want to know myself. I want to know how long I'm going to last. Maybe I don't want to know, but then that's the point. And you can start to do some analysis to say, what is the most important part in terms of machine learning, tells you the issues on how fast it's going to degrade. Obviously, the top one has previous failure. If we go to hospital more, it doesn't mean that you're not really good. So the point is that we tend to repair pipeline, more repair, you get more of that. That is big. Within the fault zone, for us, is very big. Diameter of 4-inch is very, very important as well. So you start to see some engineering through this technology. And you can do all these fancy stuff. This one is called left truncated right sensor tree based on conditional interface tree, LTRCIT. I'm not sure you understand, but I'm not sure. The only thing I can say to you is that left truncation means that I only have 30 years worth of data from 1990s to 2020. I don't have a data before that. So I have to extrapolate the data historically backwards, and then that is a left truncation, but at the same time I have to extrapolate in the future as well. So there's a technology in AI how to treat that particular problem. And you can start to do some, and many of the AI company will say, my leakage rate and my prediction is pretty good. But that is something that you maybe get the answer, but what you really want to know, what's going on behind that particular model. Just to give you a little bit of hint of this 30 years, so this is 1880s is where we start to put the pipe in the Bay Area. We only have a data from 1990s. We need to extrapolate backwards, and then we have to predict further. We can start looking at the data. We have 30 years, but let's say if we only have 20 years of data, what's the value? If we have a 30 years data, what's the value? You can look into that. If I only have 20 years later, these are different models. Sorry, it's just numbers, but then it's just a number, but then it shows you, if I only have 20 years data, what we did is that we sort of look at 20 years worth of data and trying to predict the next year whether it's going to break or not. So we have 20 years data, and then we predict what's going to happen in the next year. And then there were 685 pipes that broke that particular year. And if I have a 30 years worth of data, I can predict about 50%. It's going to break. In other words, out of 683, 700, 350, I could say, okay, let's replace it before it breaks. But it's still 50%. Whether you like it or not, that is the truth. If I only, yes. Sure.
It's very interesting. That's why I'm asking this question. You have 30 years data. So if you only use the present 10 years data,
Yes.
can you predict the previous 20 years data and tally it with that?
Yes. So if I use 30 years data, I can predict next year 50% of those, to be fair. If I have 20 years worth data only, I could only get 14%. So 20 years worth data, 30 years data make this difference. So the point here is that long-term monitoring is essential. At least for this case shows that I need 30 years to have the 50% right, 50-50. But that makes a big difference. If I have 685 pipes and I know it's going to break next year, 50% of this, I can proactively change that pipe and then save that particular one. So it becomes a more cost calculation, how this prediction can be made. So the point is that long-term monitoring is essential. Every cases are different, but at least I'll show you how we can do these in pipeline systems. And this is what we tend to do, is using those model likelihood of failure. Smart and safe city. I'm trying to come to the end. I know it's been long, so hopefully you're okay with me. What we can do is that we have a system that we can start to model the system sort of a regional scale from the road level to the regional road network, or pipeline from the pipeline level to entire pipe network as a computer simulation. And that is what we do at SimCenter. And many of the cases, I'm sure in Dubai, is that how this system, one system affects the other system. So these are called systems of systems. As an infrastructure owner, I'm only interested in my system. But then often the other system failure affects my system. But the point is that sometimes we don't talk to each other, but we don't know the consequence of each other. So often that particular benefit of working on systems of systems is very diffuse because it's very difficult to simulate that kind of scale. But with high performance computing, we can do that. For example, in the Bay Area, we have 7 million people. Every day, we have 15 million trips. We sort of know where they start and when they go. They tend to go to drop their kids and come back home. They go to the work and all these things. So we have a census record, how people are moving around. And we can model each individual car, 15 million cars, through the computer simulation. And then we can say, okay, let's stop the Bay Bridge because it's fall down. and what's going to happen to the traffic. So these are the simulations that we do, is that if these are the simulation of the entire network, and then if before the Bay Bridge goes down or after the Bay Bridge goes down, what's going to happen. So simulation nowadays, you can start do that from the road level to the regional scales. In California, we have wildfires. You may have heard about LA wildfire recently, and then we had a lot of issues in evacuation. We can do a simulation of each individual cars. So these are the cars moving around. These are agents, we call it. These are background traffic. And then we start to see a blue popping up. This is in an area called Point Reyes area, where the resident, because there's fire happening, start to see and how people are moving. So we can do these simulations. It allows us to talk to residents, say, this is you, and you're going to have a blockage over here and that. Now, in this particular site, here you have two simulations. One is when the fire goes quickly, everybody has to evacuate. So if the fire happens, we all have to evacuate. But if the fire is going slowly, we can have what we call sort of a stage evacuation, and it shows the differences. And then, obviously, you don't know which one is going to happen in reality, but the residents start to understand the complexity of the issue visually. So this is where interesting things comes in, is that we do a simulation of the wildfire. We do simulation of traffic, but we know the most important part is how people communicate each other. So this is where the social scientist comes and tell us these are the models how people react to certain messages, and then how they move, and this becomes a very important part of the model of our digital twin. We have a digital twin of the wildfire, we have a digital twin of the evacuation, but we have a digital twin of the social scientists creating how people communicate, and that creates what we call social technical digital twin. ChatGPT is insane now. We have our code running these simulations. Actually, many of the public came, Kenichi, can you do the simulation for my neighborhood? And I said, yeah, but we don't have many researchers. So we created a ChatGPT platform where residents can run their own simulations, create an input file, and then run their simulations and the output, and then the output will be visualized by themselves, and they start to learn about the issues that they have. It creates its own podcast, and then creates a personal podcast. And this is where we're going toward, is how do we make our personalized infrastructure system modeling to a personalized one that community can use by themselves to understand the complexity. So this is one of the startup that we have called WeGo. I put these slides in because in Dubai I heard that there's a threat of flooding. You have a flash flood nowadays. So this is another simulation that we did for the Shanghai metro, where you have this sort of a system. They had a problem with the flooding in Shanghai. And again, we do a simulation of the network. So we model each individual person because they have a record of when they come in and then when come during the daily. So we're doing that simulation again of that. And you can see how people are moving in and out in the simulation. And then we can start in the ordinary time, which part is very congested or not. But then we can start to see if a scenario of 5-meter water level comes out, the stations get flooded, and then it's going to have a disruption, and then which part of the lines will get disrupted, and then what are the waiting time in the platform. So you can start to do these simulations. So we start to see these as an opportunity. Of course, this is just a model, but it gives you the understanding of the bottlenecks. Once this happens, then you have to recover. So this is another one that we're really looking at, is how do we recover? And again, there's an earthquake in San Francisco. There'll be a lot of buildings that will get damaged, but the question is that how do we recover to what we call functional recovery? And it may take many, many months to come back. And here is the issue, like I said, just looking at the building, Once you get your building, you have to bring a lot of things. You want to make sure that water will be there, transportation will be applied, supply of the jobs, people, like Encardio, right? People coming to fix things, for example. So that's another demand and supply issue. Housing and all these things. So we all bring this together to look at the recovery. So again, this is a simulation of saying, okay, when an earthquake happens, which building is going to give a large damage? And you can see awaiting, rapid inspection, financing, contractor mobilization, site preparation, cleanup, detail inspection, architecture, engineering design, permitting, demolition, repair, functional. You have to go through all these things but then there's a supply and demand issue that comes out. And what we do is that we simulate to see which one will become a bottleneck, so the city of San Francisco will be prepared to what are the issues that may come up during a big event. So these are things that we engineers can try to do to highlight these issues. And so if you're interested in, we have a platform called SimCenter, so please have a look. And this is something a digital twin is coming. All right, so thank you very much for listening to me. I'm going to finish in 3 slides, and then I'll finish. I'm not sure you know this person, Sidney Brenner. He is a Nobel Prize winner in physiology, it's a medicine. In 2003, he discovered messenger RNA. It's the one that sort of helped us recover the COVID issue. You're taking maybe some of your vaccination, which is really messenger RNA, which was not used. So what he said is that mathematics is the art of perfect. Physics is the art of optimal. Biology, because of evolution, is the art of the satisfactory. If it works, you keep it. If it doesn't, you get rid of it. But then the point is that what he has done is made a step change in medical practice through the COVID vaccination. I just want to say that infrastructure is similar. Mathematics is the art of perfect. Engineering design is the art of optimal. Sorry about engineering designers, but it's the art of optimal. Infrastructure, because of complexity and the interconnectedness, is the art of satisfactory. Because it's really political, legal, economic, community constraints are very, very strong. So we have to appreciate that particular complexity. And monitoring is very, very important to ensure that we are understanding what's really happening, because it's not perfect. So future infrastructure next 100 years. This is a book, City of the 21st Century, from Amazing Story 1942. Britain in 2021, which was actually 5 years ago. And we see this. Well, Dubai is like this. I don't see any flying cars yet. Maybe next year, yes, yeah. So we're a little bit 5 years behind. But the point is that, and also if you look at it, there are no cars on the street. People just walking around. So there are no car congestions anymore in this particular world. But the point here is that we're not very good at predicting the future. But if we monitor, we can do better, I think. So we are responsible for doing the things right for the future generation, and I believe understanding how the complexity works through monitoring is what we should do. And that's all I wanted to say. Thank you very much.